So let's develop some techniques that are based on F equals ma, but that don't force us to go through the kinematic equations to solve problems. So we'll be able to solve all the problems we've seen before, or many of those problems, plus more problems that we would not be able to solve using kinematics. So these ideas are fundamentally constructed from F equals ma, and the first object that we're going to construct or invent or define is the integral of the force over a distance, and we're going to call this work. So W equals work. W means work, and we define that as the integral of the force over the distance. There's a dot product here, and the reason for this is that we're trying to get a sense of we're acting on some object with a force, let's say that way, but if the object doesn't move in the direction of the force, let's say the object moves this way, so this is the path, and we want, a differential version. We consider little bits of the path, so dr's would be this way. Say the object moved that way. Clearly, we have failed to get the object to move in the direction of the force, which is what we want. And so we want this quantity to involve this dot product. So this is the reason for the dot product. That would be equal to 0 in this case, because the dot product, of course, is the magnitude of one vector, the magnitude of this infinitesimally small vector, times the cosine of the angle between the two, and the angle between the two here is 90 degrees. So the cosine of 90 in this case would give you 0. And so it's the dot product, and the dot product, of course, gives you a number. So this is ultimately just a number. Okay, so we have our definition of work, and so W is equal to integral f dot dr, and now we're going to show that the work that you do on an object, that the work that a force does on an object, is equal to some other quantity that involves the speed, and we're going to do this by way of F equals ma. So if F equals ma, then I can, of course, say that integrating F dot dr is the same thing as integrating ma dot dr, which by way of the definition of velocity is just dv dt dotted into dr. But I can think of this as a little quantity in the denominator and just move it from one object to the other. So I can write this as m dv dot dr dt, and I can recognize that as velocity. So I get m dv dot v, and of course that's the same thing as an integral x dx, which is x squared over 2. And so this becomes, I can pull out the m and write this as v dv, and that's just a number. It's just a number like this is. And so I get m v squared over 2 as the result, and I'm integrating from some initial to some final point. So it's a initial to final, and so this becomes m v final squared over 2 minus mass v initial squared over 2. And so this quantity, mv squared over 2, is what we call kinetic energy, and the symbol for that is K. So K is what we mean by this quantity. And we call it a kinetic energy, and so work and energy are related, work and kinetic energy are related, and basically what we've just shown is that work equals a difference in K, where delta K is just the final minus the initial, and this is the work kinetic energy theorem.